Welcome to AI Frontiers, where the forefront of artificial intelligence research is explored through a comprehensive lens. This episode offers an in-depth examination of the computer vision landscape, synthesizing insights from 16 influential research papers published on May 12, 2025. The discussion will traverse emerging trends, technical breakthroughs, and the evolving real-world impact of computer vision. Whether the audience consists of seasoned AI researchers, passionate technology enthusiasts, or those curious about advancements in machine perception, the content has been curated to both inform and inspire. The episode will begin by establishing the foundational principles of computer vision, then progress to highlight dominant research themes, transformative findings, and detailed reviews of particularly influential works. Methodologies propelling the field forward will be discussed, along with the challenges that lie ahead and the societal implications of rapid progress. This journey through the next era of computer vision invites listeners to engage with the field's most dynamic questions and promising directions. To understand the significance of current advances, a brief overview of computer vision is essential. Computer vision, commonly referred to as cs.CV in academic discourse, is a specialized domain within artificial intelligence and computer science dedicated to enabling machines to interpret, process, and analyze visual data. This data originates from diverse sources, including static images, video sequences, and sensor streams such as those from event cameras or pressure mats. The primary ambition of computer vision is to replicate and ultimately surpass the visual perception capabilities observed in humans and animals. In practical applications, this encompasses object recognition, scene segmentation, motion tracking, three-dimensional environment reconstruction, and the generation of novel visual content. The far-reaching effects of computer vision are evident in sectors such as autonomous transportation, where vehicles rely on visual sensors for navigation, and in medical imaging, where subtle patterns in diagnostic scans are interpreted with heightened sensitivity. Surveillance systems, creative content generation, agricultural monitoring, and industrial automation are also being transformed by these advancements. Computer vision, at its core, is not only a technical challenge but also a philosophical endeavor, intersecting with questions of perception, cognition, and creativity. Positioned at the crossroads of artificial intelligence, robotics, and data science, progress in this field influences a broad spectrum of technological developments, ensuring that computer vision remains a foundational pillar for the future of intelligent systems. The most recent research reveals several dominant themes shaping the trajectory of computer vision. The first theme is multimodal and cross-modal learning, emphasizing the integration of visual data with language, sensor inputs, or domain-specific signals. For instance, the SLAG framework enables scalable, language-augmented three-dimensional scene understanding, allowing robots to acquire both visual and semantic comprehension of their environments. Similarly, NILChat demonstrates the adaptation of multimodal language models for the analysis of remote sensing data, showcasing the synergistic potential of language and vision in specialized domains. This approach enhances the flexibility and contextual awareness of AI systems, enabling richer interpretations and more nuanced decision-making. These developments underscore a shift toward AI architectures capable of synthesizing information across multiple modalities, reflecting the complexity and interconnectedness of real-world environments. The second major theme emerging from recent computer vision research is the imperative for robustness and generalization in real-world scenarios. Systems must be engineered to perform reliably under a wide range of unpredictable conditions, including variations in viewpoint, lighting, sensor fidelity, and even adversarial manipulations. The LAM-VIT model exemplifies this drive, as it is specifically designed to detect synthetic faces generated by diverse generative models, thereby highlighting the necessity for generalization beyond the confines of training data. The Robust Deformable Detector, or RDD, addresses the challenge of feature detection under significant viewpoint shifts, a problem central to applications such as navigation and surveillance. The collective focus on real-world reliability ensures that computer vision systems are prepared to function dependably in dynamic, uncontrolled environments where operational consistency is paramount. Efficiency, scalability, and adaptability to edge deployment constitute the third major theme in current computer vision research. As models increase in complexity, the need arises to compress and accelerate them for practical use in resource-constrained settings. Topology-guided knowledge distillation exemplifies this trend by enabling the compression of large-scale models by up to 16 times while maintaining minimal accuracy loss. SLAG further demonstrates efficiency by achieving an 18-fold speedup in three-dimensional scene embedding computation, facilitating semantic scene understanding in real time. These advancements make it feasible to deploy sophisticated vision systems on edge devices and in time-sensitive scenarios, thereby extending the reach of computer vision technologies to a broader array of applications and environments. Additional themes are evident in the latest literature, particularly the application of computer vision in medical imaging, the evolution of generative models, and the growing focus on interpretability and ethical considerations. In the medical domain, research addresses tasks such as sleep position monitoring using pressure sensors, wound classification, and anatomical localization within medical images, underscoring the field's potential to enhance patient diagnostics and care. Generative models such as Step1x3D and Dance GRPO are advancing the creation of high-fidelity synthetic content, facilitating new capabilities in graphics, simulation, and virtual reality. At the same time, interpretability and transparency are rising priorities, as exemplified by frameworks like Vistar, which introduces subtask reasoning for visual question answering, and studies that examine the societal risks associated with mislabeling in disaster response. These directions highlight the necessity for ethical stewardship and societal impact assessment as computer vision systems become increasingly integrated into critical domains. A detailed evaluation of the findings from the 16 selected papers reveals several noteworthy advances poised to reshape the field. The AEMOT algorithm, designed for asynchronous event multi-object tracking, demonstrates a greater than 37% improvement in tracking precision and recall for fast-moving, small objects using event cameras. This capability opens new possibilities for real-time robotics and surveillance in environments where traditional vision systems falter. The SLAG framework achieves an 18-fold acceleration in language-augmented three-dimensional scene embedding, enabling rapid, scalable, and semantically rich perception without compromising quality. J-SOVR introduces a novel approach to material decomposition from single-energy CT projections, integrating physics-informed spectral priors with implicit neural representation to deliver superior accuracy and efficiency in medical imaging. The LAM-VIT model achieves over 94% mean accuracy in synthetic face detection, establishing a new benchmark in the defense against deepfakes and synthetic media. Step1x3D bridges the gap between two-dimensional and three-dimensional asset generation, supporting more controllable synthesis for applications in graphics and virtual reality. Collectively, these results reflect significant progress in speed, accuracy, security, and applicability across the computer vision spectrum. Progress in computer vision is driven by a robust set of methodologies that continue to evolve in response to emerging challenges. Transformer architectures and detention mechanisms, originally devised for natural language processing, are now central to modeling long-range dependencies and complex relationships within visual data. Their deployment in vision transformers and deformable transformers underpins advances in feature detection and forgery analysis. Albeit at the cost of increased computational demands, Model compression and knowledge distillation techniques facilitate the deployment of deep learning models on edge devices by transferring knowledge from large, high-capacity models to more efficient counterparts, with methods such as topology-guided distillation achieving up to 16-fold compression. Implicit neural representations offer continuous, high-fidelity modeling, as demonstrated by J-SOVR in medical imaging, and support smoother generalization across tasks. Multimodal fusion and transfer learning enable models to leverage data from diverse domains, accelerating deployment and enhancing robustness, though care must be taken to manage domain mismatches. Reinforcement learning is gaining traction as a tool for guiding generative models according to human preferences or specific reward functions. Enhancing stability and scalability in visual synthesis. Each of these methodologies contributes uniquely to both foundational research and the practical implementation of advanced computer vision systems. Transformers represent a core concept in modern computer vision, modeling the intricate relationships within images or sequential data through adaptive attention mechanisms. They have been widely adopted in state-of-the-art architectures such as Vision Transformers (VIT), Robust Deformable Detector (RDD), and LAM-VIT, enabling breakthroughs in detection and recognition tasks. The principal strength of transformers lies in their capacity to capture long-range dependencies and nuanced patterns, making them exceptionally effective for complex vision problems. However, this versatility comes with the trade-off of significant computational requirements, often necessitating large datasets and substantial processing power for training and deployment. Throughout the 2025 research landscape, transformers are recognized as a driving force behind many of the most significant advancements. A closer look at the first selected research paper, Asynchronous Multi-Object Tracking with Event Cameras by Angus Apps and collaborators, illustrates the field's commitment to algorithmic innovation. This work addresses the challenge of tracking multiple fast-moving small objects in highly dynamic environments, a scenario where traditional cameras and frame-based tracking algorithms often fail due to latency and motion blur. Event cameras, which asynchronously record brightness changes at each pixel, necessitate new algorithms to fully exploit their output. The AMOT algorithm processes events as they are generated, dispensing with the need for batching into frames. Key features termed event blobs are detected using the field of active flow directions, constructed from the surface of active events. An asynchronous event blob tracker then follows these features over time, constructing intensity patches for each candidate object. A learned validation stage classifies and promotes objects based on their attributes, enabling tracking at the event rate for unprecedented speed and precision. The B-swarm dataset, introduced for evaluation, demonstrates the algorithm's strength, with AMOT outperforming prior methods by over 37% in both precision and recall. This approach not only validates the promise of event-based vision for robotics and surveillance, but also provides an open-source codebase and dataset, fostering further community advancement. The second featured research paper, SLAG, Scalable Language Augmented Gaussian Splatting by Laszlo Szilagyi and colleagues, addresses the integration of semantic and visual understanding within large-scale, real-time robotics. SLAG introduces a multi-GPU framework that embeds visual language features directly into three-dimensional scene representations, leveraging models such as Segment Anything Model and Contrastive Language Image Pre-training. The innovation lies in the elimination of per-Gaussian loss functions for language embeddings, instead employing a normalized weighted average to compute three-dimensional Gaussian scene parameters. This strategy enables highly parallel computation across multiple GPUs and introduces a vector database for efficient embedding storage and retrieval, essential for managing large scenes and supporting tasks such as semantic mapping. The framework achieves an 18-fold speedup on a 16-GPU setup while maintaining strong performance on semantic understanding tasks, as validated by benchmarks like ScanNet and language-embedded radiance fields. SLAG's efficient design supports deployment on resource-constrained robotic platforms, advancing the feasibility of real-time, language-aware scene perception. The open-source release and commitment to reproducibility further solidify its impact, positioning SLAG as a foundational tool for multimodal scene understanding in robotics and intelligent systems. The third research paper selected for detailed analysis is cs.CV, Joint Spectrum Estimation and Multi-Material Decomposition from Single-Energy CT Projections, authored by Qing Wu and collaborators. This work confronts the challenge of accurately decomposing tissue composition from widely available single-energy computed tomography, CT scans, a task traditionally dependent on specialized spectral CT scanners and pre-measured energy spectra. cs.CV reforms the problem by treating multi-material decomposition as a joint inference process, performing both spectrum estimation and composition analysis simultaneously. Physics-informed spectral priors are incorporated to simulate a virtual spectral CT system, improving reliability and reducing artifacts such as beam hardening. The framework employs implicit neural representation, modeling material maps as continuous functions, thereby introducing an inductive bias towards smooth anatomical structures and enhancing estimation quality. Evaluations on simulated and real CT datasets demonstrate that cs.CV surpasses state-of-the-art methods in both accuracy and computational efficiency, delivering cleaner, artifact-free reconstructions. By making advanced tissue analysis accessible with standard CT equipment, cs.CV represents a significant advancement for clinical diagnostics and medical imaging. The methodological innovation and clinical relevance of this work position it as a transformative contribution to both computer vision and healthcare. Looking to the future, the field of computer vision faces both persistent challenges and new opportunities. Data scarcity and the need to adapt to domain shifts continue to limit model performance, particularly in specialized areas such as medical imaging and remote sensing. The rapid advancement of generative models introduces creative possibilities, as well as novel security threats that demand robust detection and control measures. The practical deployment of increasingly capable models in real-world, resource-limited settings, such as robotics, healthcare, and urban infrastructure, requires ongoing innovation in efficiency and scalability. Attention to fairness, interpretability, and accountability is becoming ever more critical, particularly as vision systems are integrated into sensitive applications. Open-source initiatives, including the public release of code, datasets, and frameworks, are accelerating progress and democratizing access, fostering multidisciplinary collaboration. Future research directions are likely to include the integration of additional data modalities, advancements in generative modeling and simulation, and the refinement of scalable, interpretable, and trustworthy AI systems. The interplay of foundational research and practical deployment will continue to define the evolution of computer vision. The synthesis and review process underpinning this episode combines advanced AI-driven tools and human expertise to ensure accuracy and clarity. Content generation and linguistic analysis were conducted using the GPT 4.1 language model, while text-to-speech synthesis was performed with OpenAI technologies. Image generation utilized the Grok platform. Every effort was made to ensure technical fidelity, with human experts reviewing the synthesis for both accuracy and clarity. Nonetheless, some oversights may persist, and listeners are encouraged to consult the provided references for further verification. The integration of automated and human review processes is part of a broader commitment to transparency and reliability in the dissemination of complex scientific information. For those seeking ongoing insight into the rapidly evolving domains of artificial intelligence and computer vision, subscription to AI Frontiers is recommended. Regular updates will be provided, offering in-depth analysis and summaries of the latest research and technological advances. Community support is instrumental in maintaining the quality and reach of these resources, ensuring that state-of-the-art knowledge remains accessible to researchers, practitioners, and enthusiasts worldwide. Continued engagement will help shape the direction and impact of future episodes.